So here is your 4.5 set of notes. I'm going to start you off with that warm-up. Go ahead and press pause until you're done. Alright, so I'm going to start off. And the equation of the tangent line means that we essentially need two things. We need a point, which, let me erase that, means we would need f of, where I'm trying to find the tangent line, which is 1. That'd be 1 squared, which is 1. And then we would need a slope, which is f primed of 1. The derivative of this function right here is 2x, therefore the slope is 2. Equation of the tangent line, y minus y1 is equal to m times x minus x1. And so y minus the y of the point is equal to the slope times x minus the x of the point, which is 1. So that is actually going to be shown right here. The slope of 2 at that point would be about here. That would be the tangent line. So the tangent line then is very similar to the concept of local linearization. If you look at the 4 graphs that are down here, they're actually all of the same one graph that I showed you above, x squared. And the difference between the 4 graphs is I essentially am zooming in on the point 1, 1. So the 1, 1 point is in each of the graphs. And the difference is it looks as though I graphed something different. But what I did was I zoom in so close to that one point, we call that the neighborhood of the point, that the tangent line essentially looks exactly like the graph. And what it means is if I get to the neighborhood of a point, the curve will start to look linear. And because it looks linear, it actually looks exactly the same as the tangent line. So that's actually the concept of local linearization. So what I want you to pretty much know from this, is the fact that a tangent line, so local linearization, we usually always pick a point, we call it centered at a point, x equal to a, and x equal to a meaning, in this case, where we created our tangent line, which was at x equal to 1. That would be considered the center of the linearization. What we'll see is that the local linearization states that in the neighborhood of x equal to a, the curve will be essentially, and I'm just going to say essentially because it's not exactly linear, and will follow the graph of the tangent line. So that's essentially the concept. What I want you to understand is non-differentiable points therefore don't have local linearization. What I mean by that is if I look at the graph of f of x is equal to, easy one, absolute value of x. And we actually did this in class at one point. If I take an absolute value graph and I decide, well, I'm going to zoom in as close as possible to the tangent line at x equal to 0, well, to do a tangent line you need the derivative, and we know that f prime of 0 is undefined or does not exist. It's because there's no possible way to graph a tangent line because there's absolutely no local linearization. Meaning, no matter how much I zoom in there, it'll never look like a line. It'll always look sharp, no matter how much we zoom in. Whereas here, this graph up here, x squared at x equal to 1 looks curved, but the more and more we zoom in, it actually does end up looking linear. So, I'm going to write the notes for your local linearization. It looks like I have a little bit of an issue on the right. Let me try to fix that. Alright, all fixed. So, what I'm going to do is write the equation of a tangent line here, which is y minus y1 is equal to m times x minus x1. And then all I'm going to do is move this y1 to the other side. Therefore, I'm going to add it. And we end up with something like this. Well, if you remember how we end up getting those values, remember that your m is actually the derivative, and then the y value was f of a. So really, if I should have written a little smaller, if I rewrite this with function notation, this would be the y value at x equal to a. This would be the derivative at a times x minus that x value we call a. So that looks a little more complicated, but that's actually how you write the equation of a tangent line. Well, local linearization is exactly the same. We can literally start off with the equation of a tangent line, and I can literally move everything around and kind of follow this step right here. So I get y is equal to f of a plus the derivative at a times x minus a. And local linearization says this y value, we're just going to rename it. So if I rename it, I end up with this L. So you'll see this in the text. And this whole entire piece just means y value. It's notation written to show you where we're centering the local linearization. What that means is where you're finding the equation of the tangent line. So we just write in that point. Sometimes people will call it L of. So other times, and I'll show you that actually in the next problem. So right here, we want to find the linearization at x equal to 0. So that's this point right here. So let's start off with, the process looks exactly like a tangent line. So what I mean by that is, to start off, I would have f of 0, which is equal to the root of 1 plus 0. It gives us 1. So the point is 0, 1. That's actually your center. The derivative at 0, chain rule, 1/2, 1 plus x to the negative 1/2 power, times the derivative of the inside, which is 1. And we're going to do this at 0. So f prime of 0 is equal to 1/2 times 1 plus 0 is 0. 1. And in case you're a little confused with that, remember we rewrite. So the 2 is in the denominator. This 1 is in the denominator also. 1 to any power is going to be 1, but I wanted to show you how to get rid of that negative power. So we actually get 1/2. So to write the linearization, you're literally going to do exactly the same thing as writing the equation of a tangent line. So here we go. Y minus the y of the point is equal to the derivative times x minus x of the point. And to turn that into linearization, to use the notation, we just change the y to L of 0, 1. All this says is y equals, the y value is going to move to the right, so 1, and then plus the 1/2 times x minus 0, which obviously can be simplified. That would be the actual local linearization. Alright, so this table, to see how close the approximation is, I had to actually do this separately because I don't have a calculator on here. But look underneath, this is actually the calculator, and what you do is, actually, I got it a little back. Alright, so I fixed it. So what you see down here, and I'm going to pull it up a little bit. What you're looking at is, I actually took my calculator, and the y1, which would be here, the y value by linearization, I substituted in that y1 is equal to the 1/2, the 1 plus 1/2. 1 plus 1/2 x minus 0, and then the y value of the function, I substituted in y2 is equal to the root of 1 plus x. And what I'm showing you down here in this table, right here, is the fact that local linearization just shows that the actual, which is in red, the real function versus the tangent line in blue, that the values as you get really close to 0 are almost exactly the same. So you can notice that only negative 0.01 is a little different, and that's actually the value that's furthest away from 0. So you can actually copy this into your table in your notes, and I'll give you a little bit of time for that. Just press pause. Now the last piece here is your over and under approximation. So I'm going to start graphically showing you what an over approximation looks like. An over approximation just says that the tangent line is above the curve, and an under approximation says that the tangent line is below the curve. And what does that mean? Looking at this table, if I was to approximate, there are going to be times where your real value in red is bigger or smaller. And what we do is we can figure out if it will be bigger or if it will be smaller based on the tangent line. So, graphically speaking, if you draw a function such as this, you'll notice that no matter where I draw the tangent line, it's always on top of the curve. And then if I draw this, oopsie, you'll notice that the tangent line is underneath the curve. And what I'm showing you is that an over approximation happens anytime the second derivative is less than 0. Well, what does that mean? It means that the function there is concave down. And then same thing for tangent line being below, is because the concavity is up. So what we see is the fact that, let me get a different color here. What we're going to end up seeing is I can draw a tangent line anywhere on this curve, and every time I do it, because the graph is concave down, the tangent line is going to be on top. And what that means is if I use a tangent line to approximate a value, let's say here. Now, if this is the x value, I'd have to go straight down to find the x value on the curve. Notice the 2 points. The tangent line's point is on top of the curve's point. And again, we can use a tangent line that's already been drawn here. Pick an x value on the curve, there. Go straight down, and you'll notice that at the x value of the tangent line, it's going to be below. So my approximation using the tangent line will be less than the actual curve. Alright? So here I'm going to just do the free response question, and you're welcome to fast forward through this. All I'm going to do at this point is do the free response question, and then after that I'm actually going to do a few examples from the 4.6.0 worksheet that you have for homework tonight, which actually isn't on linearization. It's to help us with 4.6 when we return on Monday. So starting off, it says let h be a function divide for all x not equal to 0, h of 4 is -3, and the derivative is given by. So we know what the derivative is. We don't know what h is. There might actually be a point where we might not be able to do a problem, but let's see. Alright, part A. Find all values for x which the graph has a horizontal tangent. So by definition, that means where the derivative is equal to 0. So I'm going to take x squared minus 2 over x, set it equal to 0. And I get x squared minus 2 equals 0. X is equal to plus or minus 2. And I want, root of 2. And I want to determine extrema. So here, h prime, negative root 2. 0 I have to put in because that's where the derivative was undefined. Even though they didn't ask us to find that, we know that just by looking here. I'd have to find where it's undefined to do my sign chart. So undefined here. It says that it's not in the domain of the function, so I'm going to cross it out. Here's where the derivative is 0, and then in between 0 and root of 2 is 1, so I'm going to put 1 into the function, and I get negative. If I put negative 1 into the function, I get negative over negative, which makes it positive. And then if I put in a million, it would be positive. But if I put in negative 1 million, I would get negative here. Alright, so I have a, let's see, it looks like I have a minimum at x equal to negative root 2, because f prime of negative root 2 equals 0, and f prime changes negative to positive. I have also actually another minimum at, and I could have actually done these together to save a little time, and I think I will actually. I'm just going to change this to plus or minus, because the other one's also a minimum, because f prime of plus or minus root of 2, because they're the same reason. Alright, so part B, on the intervals concave up, so I'm going to look for where f double prime of x is greater than 0. That's going to be my reasoning. So, or h double prime. So, h double prime of x, I'm going to use the quotient rule, low d of high minus high d of low all over low squared. That would give me 2x squared minus x squared, don't forget to distribute, plus 2 all over x squared. So I get x squared plus 2 over x squared. Where is the graph concave up? So h double prime of x equal to 0, h double prime of x equal to undefined. Equal to 0, we get x squared plus 2 equals 0. X squared equals negative 2, which it can't. And I get x squared is equal to 0, so x equals 0. So on my sign chart, I have that at 0, we're undefined because it's not in the domain. I have negative 2, I have nothing else, whoa. And no matter what value I put in to the second derivative, I'm always going to get a positive. So where is the function concave up? It is concave up from negative infinity to 0, not inclusive, union with 0 to infinity. So I'm excluding x equal to 0 because the derivative doesn't exist there. Letter C, write the equation of the tangent line at x equal to 4. So first I need h of 4, which they gave us, negative 3. I need h prime of 4, which they gave us the derivative, so that'd be 16 minus 2, which is 14 on top, divided by 4, 7 halves. Hopefully I did that right. And then the equation of the tangent line would be y minus negative 3 is equal to 7 over 2 times x minus 4. The equation of the tangent line. And then letter D says, does the tangent line lie above or below the graph of f for x is greater than 4? So what I need to know, when x is greater than 4, what's the concavity? So f double prime of x is positive. And how do I know that? Because we did a sign chart right here. So because the second derivative is positive, I'm going to draw a concave up. I'm going to physically draw a tangent line anywhere on there so I know the answer to the question. So I can tell, because h double prime is positive, h is concave up when x is greater than 4. Therefore, the tangent line lies below. So they don't call it linearization, but we're using the same concept to figure out if the tangent line lies above or below. And if it was a linearization, it would mean that the linearization of the function at x equal to 4 is a under approximation. So I'll just write that. So the tangent line is an under approximation of the curve. Alright, so there's everything. On the next page, you'll see that there's an answer key, so you can go through and actually double check your answers and give yourself a score. If you did it with me, you end up with a perfect score, 9 out of 9. Remember, our goal is to get 7 out of 9. Alright, multiple choice example. And this would be a problem that you would actually be able to use the calculator for. Alright, so I'm going to try to go through as much as I can without the calculator, and then I'll also show you how you could end up using the calculator. So, if you notice, this is where we're going to approximate, so be careful. This is our center. So first I'm going to have to get the point at x equals 0, which would be the 4 plus the sine of 0. The sine of 0 would be the y value here, which is 0. We get the root of 4, which is 2. Y prime of 0 would be, chain rule, 1/2 times 4 plus sine of x to the negative 1/2 times the derivative of the inside, which is cosine of x. I'm actually going to rewrite it so that I know how to evaluate properly. The cosine of x is the numerator, the denominator is everything else. The 2 is down there, and because the 4 plus sine of x has the negative power, it comes downstairs. Alright, so I'm going to find y prime of 0, which would be the cosine of 0 over 2 times, we already know that the sine of 0 was 0, and we know that part right here. So the cosine of 0 is 1, and we get 1/4. So the tangent line, y minus the y of the point, is equal to 1/4 times x minus 0. So because this is a multiple choice, no one's going to look at my work, I can leave my linearization as a tangent line, and then all I need to do is approximate the value. So y minus 2 is equal to 1/4 times the x value, which is 0.12, minus 0. So really, I guess we could have done this without a calculator. So 1/4 times 0.12, and then the plus 2. Alright, so my answer becomes, let's see, I believe this is 2.03. This part is 0.03. So my answer is letter B. Alright, so at this point, I gave you a free response example, a multiple choice example of linearization, which is section 4.5. So I'm going to go through, I think, 2 homework examples. And they're actually not homework examples, they're going to be from your physical homework, just to remind you how to do the problems. So for number 1, so you're actually looking in your homework packet, the 4.6.0 worksheet. Go ahead and press pause while you look for that. Alright, so this is actually something you've already done before. I'm trying to remind you how to do it so that we are ready for related rates. So the questions almost look the same except for the respect to variable. So for letter A, the respect to variable is x, so I end up with implicit differentiation. So anytime I take the derivative of something that's not an x, I get a dy dx here equals 0. And how do I get that? It's because this would be a chain rule. So I would get 2y, and then I have to take the derivative of y with respect to x, and that's where this differential comes from. And then dy dx is equal to negative 2x divided by 2y, so negative x over y. So what's the difference? Well, because now we're doing a t, when I take the derivative of x squared, I would get 2x times the derivative of x with respect to t. When I take the derivative of y squared, I get 2y times the derivative of y with respect to t, and then equals 0. And then I want to solve for dy dt, so I get 2y, I'll do this in 2 steps here just because there's a lot. Negative 2x x dt, and then I'm going to divide by 2y, which cancels the 2's, and I get negative x over y times dx dt, which also is the same thing as you writing negative x dx dt all over y. You don't want to split up the differential, you want to keep that together, so you don't have to get a common denominator. This would not be considered not simplified. That's just because the fraction is a result of a differential and we want to keep it the same. Alright, number 2 and 3 and 4 are all up to you. Just be careful with your respect to variables. Okay, and then I'm going to actually do one more example. Let's see, which is from this one. We'll start off with, I guess I'll do this one down here. So, part A says, find dy dt when x is equal to 8. So we're doing this with respect to the variable t. So this would be a product rule. So first one, this letter A, first one, derivative of the second with respect to t, plus the second times the derivative of the first with respect to t is equal to 0. And because I'm just going to be solving, I can substitute in my values here. And I end up with dy dt is a question. dx dt is 10. Let's see what happens. So 8 dy dt plus y times dx dt, which is 10. And right now I have two variables, which is not okay. I can't solve it. But if we know that x is 8, I can go back to the original, substitute in my 8, and get how much y is at that same time. So y is equal to 1/2 when x is 8. So y is equal to 1/2 equals 0. So I get the dy dt is equal to -5/8. So this information right here, we needed it to also find the y value. Okay? There's everything you need for 4.5 plus the homework. See you guys on Monday. Make sure homework number, I believe this is 15, is done for Monday.